All right. So, morning, guys. Sorry for some technical issues. So, this time we're going to finish up the class contents and then do a quick review, as I said. So last class, we mainly discussed the meteorology, right? So we spent quite a lot of time to talk about the Earth's atmospheric circulation. So this is very important because whenever we discuss the air pollution, we have to consider where the wind is, right? Because if we're living, let's say, upwind of a coal-fired power plant, we don't necessarily need to worry about the air quality because on the air pollutants are not going our way, right? So that's why we discuss why there's wind, right? And what are the general patterns for the wind in our atmosphere. So we mentioned that on our Earth, basically there are 6 cells, right? So there are 3 cells on the northern hemisphere and 3 cells on the southern hemisphere. So we have the Hadley cell, which is recirculating air in this way, right? And the polar cell, which is recirculating air in this way. And due to these 2 different cells, there has to be another cell in the middle where the air is moved. Basically, the direction is decided by the direction at the polar cell here, and also at the by the Hadley cell at the equator. Right, so that's why we have 3 cells on the northern hemisphere and similarly 3 cells in the southern hemisphere. So further, we introduced how the Coriolis force is affecting the general wind circulation. We mentioned that at the equator, the wind is blowing from east to the west. We mentioned mainly because of the Hadley cell, the general wind pattern is in this way. But because of the Coriolis force, everything is going to bias right on the northern hemisphere. Remember, because we're living on the northern hemisphere, so we're always right, correct? So because of that, the wind is going to get diverted to the right, and then we're going to have the general wind pattern from east to the west. We mentioned that there's an application from this Coriolis force, which is the direction of the hurricane here. So if I just give you a quick quiz, so can you guess or can you analyze where is this hurricane located? Is it in the northern hemisphere or is it in the southern hemisphere? Okay, 5 more seconds. Okay, we'll stop here. So I think more than half is correct for this question here. So the general understanding is that we need to really analyze how the wind is blowing for this hurricane system. Right? So we know that the hurricane system at the center is a low pressure center. So that's why the general wind direction is going to be from outside to the inside, right? And then let's assume that we're on the northern hemisphere. So if it's on the northern hemisphere, then the wind is going to blow this way, right? Bias to the right, which is against the direction that's shown here, right? It's against this direction, which means that this should be on the southern hemisphere because on the southern hemisphere, the wind direction is going to get diverted to the left, right? So this is following the direction that's shown in this hurricane here. So this is the southern hemisphere. So just to make sure that you guys understand this, let's do this quiz again. 5 more seconds. Okay, stop here. So I think we should be good for this question here. So I mentioned that this Coriolis force has some application on our Earth. So basically, it also has some applications in the space, right? So we know that this is the Jupiter's red spot. So this is a very huge anti-cyclone system. Anti-cyclone. So anti-cyclone is a little bit different from the cyclone systems or the hurricane systems on that are shown in here. So basically, if you remember, for the cyclones or for these hurricanes, it has a low pressure center, right? At the center is low pressure, and at the outside, that's higher pressure. At the surrounding of this low pressure center. So the anti-cyclone means at the center, it's a high pressure, while outside is low pressure. Okay, so what this means is that for the anticyclone, the wind direction or the targeted direction of the wind is going to go this way, right? And then if you further check, actually the Jupiter rotates in the same way or in the same direction as the Earth. So it also rotates in this way from the west to the east, okay? So what this means is that the Coriolis force is going to do the same thing on the wind direction or the wind pattern on Jupiter compared to the Earth. Basically mean if you live on the Jupiter, then everything is going to be diverted to the right. And if you live on the southern hemisphere, then it's going to be diverted to the left. Okay, so let's try to analyze whether this wind direction works or agrees with what we understand. Okay, so basically this Jupiter's red spot is located on the southern hemisphere. So if it's on the southern hemisphere, it's going to get diverted to the left, right? Which means that the wind is going to get this way. Okay, so which means that this direction or this general recirculation here should be clockwise. This is counterclockwise. Right, so if you check this shape here, right, this means that it's counterclockwise. So basically the wind is going this way. Right, you can also see that here. Okay, so the Coriolis force can apply to many systems, not only on the Earth, right? So this is another example we can show here. So at the end of last class, we mentioned that for the transport of the air pollutants, if we talk about their different directions, let's say from north to east, from north to south or south to north, it's normally going to take a longer time. But if we talk about it from east to west or west to east, then that's going to be much faster, right? So we mentioned that the pollution that's coming from North America just need around 2 weeks to get transported to Asia. Well, the pollutants, if we want to transport it to the higher altitudes or to higher latitudes or to lower latitudes, right, to the equator or to the polar region, that's going to take several months. And if it wants to go across the equator, that's going to take a year. Right? This is a horizontal transport of the air pollutants. And if we talk about the vertical transport, that's also going to be quite different. We mentioned the concept of the planetary boundary layer, right? That's just a layer that's around 1 to 3 kilometers above us. And I think this layer, almost all of the people live in this layer here. So for the air pollutants to transport within this layer, it just needs 1 to 2 days. But if we want to transport something further up, higher than this layer, that's going to take around a week. So we mentioned that the lowest layer of the atmosphere is called the troposphere, right? So if we want to transport something to the upper troposphere or to the tropopause, that's going to take almost a month. And if we want to transport something to the stratosphere, okay, so that's going to take much longer here. We mentioned that the ozone is located in the stratosphere, right? So if we talk about the CFC that's being emitted on the ground, that's going to take 5 to 10 years for the CFC to go up to the stratosphere. And also for things that are transported down, that's also going to take a relatively long time. It's around 1 to 2 years, okay? So we also mentioned the island effect. So this is going to be some regional effect that's due to the temperature difference, right? So generally the islands are warmer, right? So that's why you have the humid air that's transported from the ocean to above the island, and then you're going to form some clouds at the top. So the same thing is going to happen to cities, right? So if we have a crowded city in the center, and then some suburban or rural area at the outer region, and then because here we have a higher temperature, right? So the air is going to rise up at the center, and then also the air in the suburban area is generally more humid, right? So we're going to form these cloud coverage over the cities. Okay, so these are also going to affect how the transport of the air pollution will be, right? For example, if there's a coal-fired power plant that's sitting here, okay, emitting plumes, then people living in this area, further away from the city, they don't need to worry too much about the air pollution from the power plant, right? But the people in the cities, they might be worried about the power plant air pollutants. So last class, I think we stopped at here. So this is basically trying to show how does the pressure or how does the temperature evolve as a function of the altitude. So here, the altitude is shown in kilometers, okay? So if you recall, when we introduced the planetary boundary layer, that's generally 1 to 3 kilometers above us, right? So we're talking about really low level here where people is living, right? And then basically, if you look at the pressure, then the pressure is going to decrease almost following a logarithmic scale. Okay? So it's going to decrease exponentially. And this indeed makes sense because let's imagine this is our Earth, right? The atmosphere is denser at the surface of the Earth, while the atmosphere is much thinner further away from the Earth. This is due to the gravity, right? So that's why the pressure further higher up is going to be much lower. But in terms of the temperature, it's showing a quite interesting feature. So within the troposphere, if you see, the temperature is decreasing almost linearly until it hits the boundary between the troposphere and the stratosphere. Okay, so again, the stratosphere is where ozone is located. Okay, so you see that basically we're having this almost linear decrease. And then at one point, the air is not going to, or the temperature is not going to decrease further, and then it starts to rise up. So the decrease of the temperature is quite easy to understand. If you think about you're going hiking, climbing a mountain, so generally the temperature at the top of the mountain is going to be colder, right? It's going to be lower. And this is mainly because you're sitting at a higher, basically higher above the ground, right? So this is a mountain, right? The ground is generally warmer, right? While at the top of the mountain it's going to be cooler, right? And then what happens is if you further go up, let's say generally between 5 to 15 kilometers above the ground, the temperature is going to rise. So this rise of the temperature this increase of the temperature is actually because of the ozone layer that's protecting us. So if you recall what we introduced about the function of the ozone or the stratospheric ozone, that is, major function is it's blocking the UV radiation, right? And if you recall or check the equations or the chemical equations we wrote, so for this reaction between the UV radiation and the ozone, the final product is heat. Okay, we're converting some high energy radiation to heat, which is another form of the radiation, right? So because of this reaction or the ozone layer, the temperature is going to warm up in the stratosphere. But we don't really need to worry too much about this higher temperature because no one is living in this layer, right? It's around 8 to 15 kilometers until, let's say, 50 kilometers. And then further higher up, because of the reduction of the ozone, basically we don't have any more ozone further higher up. So the temperature is going to decrease again. And this decrease of temperature is similar to the mechanism for the decrease of temperature in the troposphere. And we call this layer as the mesosphere. This is already very far away from the Earth, right? So since we explained why the temperature is going to rise up in the stratosphere, so I wonder if you also thought about why the temperature is going to cool down in the troposphere. Okay. So if we just imagine the movement of an air parcel, if you think about there's let's say we have a balloon of air, okay, and we're releasing it at the ground of the surface, or at the surface of the ground, okay. So then let's imagine that this balloon tries to rise up under some natural conditions. Okay, let's say that we give it a force, right? We give it a velocity, it's going to rise up. So one thing we know is that the pressure at higher altitude is going to be lower, right? So what that means is this balloon is going to expand when it rises up to a higher altitude. Let's say when it rises to here, the balloon is going to become larger, okay? So if it becomes larger, then what that means is it's going to do some work to the outside. Okay, if it does work to the outside, then that means basically we need to convert some of its internal energy. This is according to the energy balance, right? If it does work to the outside, then it has to convert some of its internal energy to this work, which is causing the reduction of the temperature. Okay, so we can think of, let's say, just two different locations. For example, we're talking about this relatively lower location. Right? This is according to the height. Okay, this is the initial location. And this is a higher up location here. Okay, so the balloon rise up for this part of the distance. Okay, so during this time, basically we need to do some work to rise it up. Let's assume that the mass of the air within the balloon is m, okay? And let's also assume that this is dz, right? So the work that we do this balloon is basically mg multiplied dz, okay? This is how high it rises up. So while during it, the process while it's being raised up, it has to do work to the outside, right? So basically this is the work. Okay, we'll also mention that the work is coming from the internal energy. What that means is basically it's coming from dT multiplied by m multiplied by Cp. Cp is the heat capacity. Okay, so basically we can have this relationship here. And we also know that the temperature is going to decrease. So that's why we have to put a negative sign here. Okay, so if we rearrange this equation, so m and m is going to cancel out, right? So we're going to have dt divided by dz, or minus dt divided by dz is going to be g divided by Cp. Okay. So this equation is going to determine how the temperature is going to decrease as a function of height. Okay, so if you further check the value for the G and Cp, we know that the G is around 10 meter per second square. Okay, so actually it's 9.8, right? So the Cp is around 1,000 joule per kilogram per Kelvin. Okay. So with these two parameters, so basically on the left-hand side, it determines that the unit for this term here is Kelvin per meter. Okay. So if you plug in these values, then we can get, what we can get is minus dT dz is going to be 0.01 Kelvin per meter. So what this means is that if we rise up this balloon by 1 meter, the temperature within the balloon is going to decrease 0.01 Kelvin. 0.01 Kelvin is quite a small value, right? We cannot really feel that. But let's say if we rise up for 100 meters, if it's rising up for 100 meters, you can feel that already. That's 1 Kelvin's difference, right? If you climb up the Mount Everest, right, and that's around 800 meters or 8,000 meters, so the temperature is going to decrease for around 80 Kelvin. So that is going to be a further higher or further larger change of the temperature. Okay, so basically this is how the air temperature is going to decrease under the natural condition. We're imagining there's a balloon, right? And then when it rises up, its temperature is going to decrease. And that's why the temperature has this pattern here. Basically, it starts from around 300 Kelvin at the surface, right? And then as the altitude or as the height increases, the temperature is going to decrease following this rate here. And we also call this rate as the dry adiabatic lapse rate. Okay, so this is the theoretical change of the temperature as a function of height. Okay, the reason why I say it's theoretical is because there are a lot of processes that can change the actual distribution of the temperature. For example, if you just place a heater outside on the ground, right? If you have a heater on the ground, then the temperature will become higher on the ground. What that means is if you just show the temperature above that heater in terms of height, so maybe at the higher altitude, it's still going to follow this trend, but at the bottom where you place that heater, the air temperature might become this way. Okay, so this is the actual distribution of the temperature. Or if you have a cooler on the ground, then it might have this distribution. So the example of heater and cooler is just showing, it's just giving some simple examples of how the actual distribution of temperature might be different from this ideal situation. But the solar radiation can also change the distribution of the temperature. And we're going to introduce that later. Okay. So the reason why we introduced the dry adiabatic lapse rate is because it affects the stability of the atmosphere. Okay. So we mentioned that the temperature of around 1 Celsius or 1 Kelvin per 100 meters, this is a dry adiabatic lapse rate, right? So if the ambient or the actual temperature lapse rate or the actual temperature decrease follows this dry adiabatic lapse rate, then we call this as the neutral condition because everything follows this theoretical condition, right? This is what we mentioned. Basically, we're talking about the actual ambient air that's following this temperature change here. Okay, so in here, the dry adiabatic, this means that this is basically the ideal or the calculation that we just showed earlier. So this gamma here is basically -1 Kelvin Celsius per 100 meters. Okay. So what we're trying to say is that if the ambient lapse rate or the actual temperature lapse rate follows this dry adiabatic lapse rate, then we call this as a neutral condition. So there are some scenarios where the actual ambient lapse rate is different from the dry adiabatic lapse rate. So here I'm still showing the dry adiabatic with the dashed line here, okay? So what this is showing is going to be similar to the situation where we place a heater on the ground, okay? So what happens is the actual ambient temperature or the profile of the ambient temperature is actually higher on the surface, okay? If you see on this end here, if we extend this line, okay? So the actual temperature is higher than the theoretical temperature. That's predicted by this dry adiabatic lapse rate, okay? So what this means is that it's going to, when the air is trying to move around, then it's going to follow a certain pattern, okay? So let's imagine that this amount of air, the air that's located at around 100 meters above the ground, tries to rise up, okay? So if it rises up, let's imagine that balloon again, okay? If it rises up, it's going to expand to a larger volume at a higher altitude, right? And it's going to still follow this equation here because the gravity and the heat capacity didn't change at all, right? So what this means is that if the air at 200 meters rise up, then when it rises to 300 meters above the ground, basically it's going to have a temperature that looks like this, okay? So the temperature is going to be higher than the temperature surrounding it, okay? So we mentioned earlier, if the temperature is higher, then that means it's going to have a lower density. If it has a lower density, then this air will try to continuously rise up, right? Mainly because it's going to have a higher buoyancy there, right? So if it further rise up to the location at 400 meters, so if you compare against the actual temperature, it's still higher compared to the surrounding air, okay? So what that means is that this air will continuously rise up, okay? So that's why we call this condition as the unstable condition. So when the dry adiabatic, when the ambient or the actual temperature lapse rate is smaller compared to the dry adiabatic lapse rate. Okay, so basically, if it has a negative 1.25 Celsius per 100 meter, so the air is going to be unstable, and then it's going to continuously rise up. And this is going to create an unstable condition. And we can also have a very stable condition, which correspond to the actual ambient lapse rate that are larger than the dry adiabatic lapse rate. For example, if it has a value of 0.5 Celsius per 100 meter, okay? So what this means is that it's going to be similar to the scenario where we put a cooler on the ground, okay? If we have a cooler on the ground, then the temperature is going to be colder than the theoretical value. Now let's imagine this amount of air is rising up. So if it rises up, still following this equation here, right? The gravity and the heat capacity didn't change at all, right? It's still going to decrease at a rate of 1 Celsius per 100 meters. You can see that when it rises up, it's going to follow this line here. And when it gets to here, let's say this is our balloon, right? It expands larger. So when it gets here, if you compare the temperature of the air within the balloon and the temperature that's at the ambient, that's surrounding it, right? So the temperature is lower compared to the surrounding air. If it has a lower temperature, it has a higher density. What that means is that the balloon is going to drop down, right? So basically it means that the air at the surface of the ground is not going to be able to rise up. So this is going to be a stable condition, okay? So basically this is comparing the ambient lapse rate, which is the actual condition, right? Compare that against the dry adiabatic lapse rate, which is the ideal condition. You can see that if the ambient condition has different lapse rates, whether it's higher or is lower than this dry adiabatic lapse rate, then the air stability will be quite different. Okay, so now if I ask you a question, which condition is the best? Which condition is the best condition for reducing the air pollutant concentration? Is it neutral condition, unstable condition, or stable condition? Okay, so we'll stop here. So maybe this question is not phrased very well. Okay, so the correct answer should be unstable condition. So let's imagine the situation. Let's say we have a coal-fired power plant at the ground. Okay, so if we have a ambient lapse rate that follows this unstable condition, what this means is that plume that's generated from the stack can rise up continuously all the way up to the top of the troposphere even. Okay, so we mentioned that humans are just living at the very bottom of this troposphere. So what this means is that we can quickly dissipate all of the pollutants into the atmosphere. And then that's going to reduce the concentration in the layer where human lives, right? And if it has a stable condition, then what that means is that the plume are just going to stay at where it's being generated, right? And it's also at a very high concentration. And now if you have a wind, then that's going to blow this highly concentrated air pollutants all over the place. And this is not good for reducing the concentration of these air pollutants. Okay, I hope you guys can understand this better. So I can relaunch this polling and then see if you have questions. All right, we'll just stop here. Okay, so it should be the unstable condition. We should say that we like this unstable condition for reducing the impact of all the air pollution here. Okay. So as I said, when we introduce these cases, we're saying that we're putting a heater or a cooler on the ground, but under the actual situation, the solar radiation can create this temperature difference or the actual profile of the temperature. So let's think about the scenario where we have solar radiation at 3 p.m. Okay, so at 3 p.m. basically the air, as the solar radiation is penetrating all the clouds, right? Normally we'll feel that temperature is hottest on the ground at around 2 or 3 p.m. Okay, so the entire atmosphere is warmed up, and under that situation, it's going to follow this dry adiabatic lapse rate. Okay, it's going to follow that lapse rate there. So now let's imagine that basically the time goes by when it reaches to around 6 p.m. when we have the sunset. So if we have the sunset, then the direct impact on the temperature is that the ground is not receiving any radiation anymore, right? And the ground temperature is going to decrease. And we're going to have basically a lower temperature on the ground while the atmosphere is still quite warm because it's not going to transport that amount of heat to anywhere very quickly, okay? So further, if we go to 9 p.m., right, it's going to have a temperature that looks like this because the temperature at the higher altitude or at the higher height are conducting the heat to the ground, right? And then the temperature is going to be further cooler, right? At the same time, these heat are being radiated back into the universe. And further, let's say this is 0 a.m., okay, 12 a.m. right? The temperature is going to look like this. So now let's imagine this balloon rising scenario again, okay? So let's say if you're releasing a balloon at the ground that has a relatively smaller volume, right? And then if we're going to follow that equation again, the gravity and the heat capacity didn't change, right? So the temperature is going to be following this line here. When it rises up, temperature is going to cool down. And now if you compare that temperature to the temperature surrounding this balloon, so the temperature is cooler, right, compared to the surrounding air. What that means is the air is going to be denser in this balloon, and then it's going to fall down, okay? Which means that basically at night, we're going to have stable condition being created for the atmosphere. So that is why you can see a lot of these pictures basically during night, okay? So this is the July 4th fireworks in DC, right? You see fireworks create a lot of particulate matter, right? But these particulate matter are not rising up to the higher atmosphere. So this height is probably just a few hundred meters, right? So let's say this is the ground. So the building maybe 100 meters maximum. So this may be around 500 to 600 meters, right? The plume is not going to rise up to the atmosphere, mainly because we have this stable layer being created. We have this stable atmosphere. It's not going to penetrate through the atmosphere and further get dissipated. And then because of that, people are going to smell this fireworks, right? And this is because of the stable condition. So we can also see pictures like this, right? So this is over a village, right? And this is during early morning. So during early morning, our ground is not warmed up either, right? So it may, if we come here, so over the entire night, the temperature is always going to decrease until early morning, right? The temperature is going to be the coolest, right? So that's why we're also going to create this stable layer. So the plume coming out of houses are not going to get dissipated. And all of them are basically trapped in this layer here. And we call this as the temperature inversion. Or this layer here, we'll call it as the inversion layer. Okay. So this is another example. So this is the inversion layer over the San Francisco Bay. So basically you can see that there's a very low layer of air where the pollutants are not being transported outside this layer. And this is basically standing on a mountain, right? So the air on the mountain is penetrating this layer because this layer, as I said, is just a few hundred of meters, right? So typical mountain is higher than that. And that's why on the mountain, the air is much clearer, while within this inversion layer, the pollutant concentration will be very high. So that's why we want unstable condition to release this amount of air pollutants, okay? So you can see that whenever we have this temperature inversion, the pollutants are not going to get penetrated through this layer here. So if you further pay attention to this, this temperature profile here, you see that the temperature basically, you have this angle here, right? So whenever you have a temperature profile that has this increasing, basically as a function of altitude, if you have a temperature that's always increasing, then you're going to create this inversion, right? The air is not going to get floating or get transported, get penetrated through this layer, mainly because theoretically the air temperature should be decreasing while the ambient temperature is increasing. So that's why it's always going to fall down, okay? So whenever you have a section of temperature that looks like this, you're going to create an inversion layer. You're going to create a stable layer, okay? So now let's think back on the atmospheric temperature in here. So this is showing the temperature as a function of altitude in much longer scale. Okay, so you see that the temperature in the stratosphere has this increasing feature, right? So because of that, the stratosphere is a huge inversion layer. So what that means is that the pollutants that's within this troposphere is going to be very difficult for it to penetrate through this inversion layer, right? So that's why when we go back here, when we talk about the transport of the CFC into the stratosphere, right? It's going to take 5 to 10 years. And this is mainly because we have this very thick inversion layer that's on top of this troposphere here. And everything is based on the temperature, right? So now if I ask you a question, so can we build a higher stack to reduce the air pollutant concentration? So the answer should be yes, right? Because we mentioned that the inversion layer is just a few hundred meters. So if we have a stack that's higher than this few hundred meters, then we can release all of these pollutants or basically get them transported more efficiently. So that's why it involves the design of the stack. So if you had taken the 2601, I think you already did some calculation on this. So here we'll just briefly go through the design methods, okay? So basically when the plume dissipates, the scale of it, basically the width and the height is also going to increase. So people created a Gaussian model to predict the transport of the plume. So basically if we imagine this is a stack here, right? And then when it releases the air pollutants, the concentration is going to be the highest at the center of the plume, while the concentration is going to decrease at the outer region, right? And then at the same time, while it's being transported, this distance here is also going to increase. So that's why we call it as dissipation, right? So people created this Gaussian model to predict the concentration of the air pollutants. So basically, along the y-axis, or along the y direction, you can see that the concentration is at the highest, at the center, lowest at the outer rim, right? So that's why we have this exponential term here. This is a Gaussian distribution. At the same time, along the z-axis, we also have this Gaussian distribution. Okay, so this is two Gaussian distributions adding up together. And the spread of this Gaussian distribution, the sigma y and sigma z, really depends on how stable the air is. Okay, so you can find out the values of sigma y and sigma z based on the stability categories. Okay, so in general, let's say during the daytime, if you have a very strong solar radiation, basically means that the ground temperature is high enough, right? So it's going to create a more unstable condition, right? And then if you also have a very strong surface wind, then it's going to be easier for the pollutants to get dissipated, get transported. So basically, we're categorizing all of these stability conditions during the daytime, nighttime, based on the surface wind speed. So based on these categories, we can refer to the values of the sigma y and sigma z based on their stability category. So basically, the 8 category, the category of A here means the most unstable condition. That's why it has the largest sigma y, right? And also it has the largest sigma z here, right? So I would say that's all for the contents of the meteorology, and that's all for the contents of the entire class. So we can use maybe just a few minutes to go through the like a quick review of this second half of the semester. Okay. So we first talk about the sulfur dioxide control. So we mentioned that there are basically 2 ways to control the sulfur dioxide. One is a fuel desulfurization, and one is a flue gas desulfurization. And specifically for the flue gas desulfurization, we mentioned or introduced the limestone scrubbing. okay, limestone scrubber, which use the stoichiometry to remove the sulfur dioxide. So we calculate the alkalinity, or the basically the amount of carbonate ions we can provide to this process, right? And based on that, we can calculate the feed rate of the limestone and also the production rate of the sludge. And this is related to the impurity of the limestone in there. So we also have a few homework problems on this. So regarding the NOx control, I think a lot of these are based on concepts, right? So we mentioned that there are thermal NOx and also fuel NOx. So there are 3 strategies to remove or to reduce the NOx formation during combustion. So that's why we have this in-combustion control methods. Specifically, we mentioned the overfare air, right, to reduce the NOx formation within the combustor. And then regarding the carbon dioxide control, we mainly talked about the calculation of the carbon emission. We mentioned that generally people will use the unit of gigatons, right, to evaluate how much carbon dioxide we emitted. And regarding the VOC control, we mainly talk about the removal by condensation, and this is using the definition of the vapor pressure, right? So basically, we can reduce the temperature of the flue gas to condense the VOC and then further collect it. I think your most recent homework problems are about this question here. And also, we introduced the absorber design. So inside the absorber, we need to refer to the capacity curves of the activated carbon, right? So an example can be, so here I'm first showing this vapor pressure as a function of temperature. You have to get familiarized with this table here, because we can use that for both the removal by condensation, and also we need to use that for the absorber design. Okay, so an example can be here, right? So our target is we're trying to remove certain amount of VOC from the flue gas stream, right? We normally will provide the concentration of these VOCs in the flue gas and also the volumetric flow rate. So we can calculate how much of these VOC we have to absorb. And then in reality, we need to further calculate how much activated carbon we should use to absorb this amount of VOC, right? So generally we'll use a capacity of around 30% because we don't want to use all of this active carbon, otherwise it's going to get saturated. And we also designed 2 beds, right? Basically 2 absorbers in parallel to absorb these VOC species. So this is your most recent homework problem. So I'll try to grade them out on Friday, and I'll also post the example solution for you to prepare the final exam. So again, I want to say that you should focus on the homework problems, okay? So it's going to be quite similar to the midterm exam. So I didn't review the contents for the PM, mainly because we did that during the midterm, right? So as I said, the final exam is going to be comprehensive, and it is a 1-hour exam, and I think the number of the problem is going to be quite similar to the midterm exams, okay? So I think I can use the final minute to post some shameless self-advertising for my group. So I think some of you might be familiar with my group because I think some of you are taking Dr. Birkin's class on research, conducting the scientific research. So I think some of my group members give a presentation about evaluating masks. So here I'm showing all the group members we have right now, and I hope you're interested in becoming a member of us, right? So here I just want to quickly mention that a series of recent accidents are putting our aerosol scientists quite busy, okay? So the wildfires, for example, the wildfires in the Western US is still going on. It's dumping a lot of particles, aerosols into the atmosphere. We have to know what is the health impact and the climate impact of these particles. So last year we had the vaping problems. This is also related to aerosols. And we're collecting a lot of data about the electronic cigarettes. So people are also very interested in urban pollution. So in our group, we designed air quality sensors to basically monitor the air quality in cities, right? And also in the underground mines. And I think the most important thing right now is the transmission of the COVID-19. So we're also doing quite a lot of related work on these projects. So if you're interested in any of them, please feel free to contact me. I know that some of you might be graduating this semester, or some of you are graduating after next semester. So if you want to do independent study, undergrad research, experiential learning, so feel free to contact me. And you can also use this website to follow what we have been working on. And there's always some project that we need your help, okay? So that's all for the contents of this class. And thank you all for following me during the entire semester. So next class, as I said, I'll still be there, but this is going to be mainly, I would say, an extended office hour. So if you have any questions, last minute questions, so I hope it's not about the calculation of the cold feed rate, okay? So if there are some last minute questions, we can always discuss that. You don't have to be there if you don't have any questions, or if you decide to work on your project during that time. So that's all for this class. And if I don't see you this coming Friday, I'll see you next Monday. All right. Thank you all.